Okay, good afternoon and good evening. I'm going to do a very quick review, making the assumption that you're probably doing this on Sunday night, and it's been 2 days since you looked at this, so I'm going to do a very brief review of the first two things that we've done and then dive in. So again, we're trying to find a relationship between the potential and the radius. That is our end goal, and so what we're doing is we're using two different geometries today. We're going to use the cylinder geometry. Your job is to derive the spherical geometry. You will use the same steps. You will just be using a different geometry. So the Gaussian surface there is shown in red, and we implored or used Gauss's law to derive a relationship between our electric field and the radius. So a couple of things that I do want you to notice about it. First thing that I want you to notice is that all of this jazz right here, that's just a constant. That's just simply a number. We don't know what that number is, but it's just a number. And then this guy right here, that's our variable of how the electric field varies with radius. So then our next step is to derive an expression for the potential difference, right? So that's going to be our potential difference in terms of, again, Q, and that should be a capital L. I know that looks like an I, so let's not make that confusing. Q, L, and R, using that relationship between potential difference and electric field. So we started that already, and remember, our path of integration is shown in blue. It's going from the outside ring to that inner center, and we are going to want the expression for the potential at the point of R. So that's shown there in red, and that red is where that Gaussian surface was. So we have two integrations using a surface as a cylinder, and then we have a line integral, which that path is from the outside towards the inside to that Gaussian surface. All right, so what we do is we look at our limits. We said our B, remember, is that outer ring. That's the location of B. We're going to integrate from B to R. And we are going from that outside, again, to that Gaussian surface. Okay, so we take our electric field expression from our previous page and we stick that in here, right? So that's this right here, okay? And you'll notice that between the electric field and the line integral, there's a dot product. And the angle between the electric field shown in green on the diagram and the path of integration shown in blue on the diagram is 180 degrees. So therefore, we can take that negative and that negative goes away. And so then we come down and we have this expression, right? So we're working from this expression right here, which is, we pulled our constants out in front, right? We said that the Q over 2 pi epsilon times L, that's just a number, right? And then we are going from B to R, and then that's proportional, or we need to take the integral of 1 over R dr. Now, we are going to define our zero potential, so we're just going to simplify this a little bit. We're going to define our zero potential. Remember, potential is what you measured using your voltmeter. A volt is a measure of potential. And so zero potential is going to be located at point B, right? So that outer ring had the lowest or the zero potential. It was at the bottom of the hill. So therefore, we can get rid of the delta. We're just going to really measure the potential with 0 being that outer ring as that function. Okay, the second thing I'm going to do is I'm going to simplify my expression a little bit. I'm just going to take this guy, I'm just going to call it a number so I just don't have to look at it so much. I'm just going to call it, what is that? I don't even know. I think that's not alpha. It's some Greek letter. Don't worry about it. It's a Greek letter. It looks like that. I think that it's not alpha. It's something else. It'll come to me. We're going to just replace it just so we don't have to deal with it so much. So here's my simplified expression. Okay, so we got that number junk out in the beginning. We call that Greek letter, little squiggly, whatever. You could call it whatever you wanted to. Again, we're integrating from that outer ring to R, 1 over R dr. And when we integrate that, we are going to have that potential is equal to that constant. And then this is going to be the natural log of R, and we're going to define it, or we're going to evaluate it from B to R. Right? We're going to evaluate it from B to R. So then it looks like this. Okay? Hopefully you're with me to there. Now, you should realize that there's a natural log property that that subtraction is also the same thing as this. Right? There's a property of natural logs that says the natural log of R minus the natural log of B is equal to the natural log of R over B. Right? That's just a log property. If you need to look that up, go ahead and look that up. Okay, so we are so close to being done, we can smell it, right? We can smell it. So our next step is going to be, and I'm going to take a minute and I'm going to get that expression right there. And I'm going to go to the next page because what we want to do is we want to figure out what that constant was. Why didn't that? I really seriously thought that I didn't I copy that? Copy. Paste. Yay! Move that a little bit over there. Okay. So our next step is going to use the expression and the measurements of the outer radius and the inner radius and Dmax to find that coefficient. Okay, so essentially what we're going to do is we are going to put in the value for that guy right there, right? For our maximum potential difference. That maximum potential difference, remember, happened from A to B, right? That potential difference happened here, and I believe we used the value of 10.07 volts, 7, right? 7 volts. And then this R, that radius would be A, this value would be B, and then we're going to solve for that constant. So go ahead and just pause for a minute and do that. Okay, so that letter's gamma. I just figured that out. Sorry for that. Okay, so we're going to sub in. We'll do 10.07 is equal to gamma, our constant, times the natural log, and then we'll just put in our values. Our R is our value for A, 0.007 over 0.076. And when we solve that down, you are going to get something that is a negative number. And it's like -4 something. All right, so when I did that calculation, I got -0.422. Okay. So then, once you've gotten to that point, then you can just simply start doing a little substituting back into your original expression, and then we get our equation. So again, we're going to go back here. We'll say V is equal to, so the potential as a function of radius, so if you wanted to even put that as a function of R in there, you can certainly do that, right? As a function of R is equal to. We get our constant value up front, so that was a -4.22, right? And then that's the natural log of R over the value of B, and the value of B is 0.076. Another way to write that would be to just take 1 over 0.076, so that you just have a coefficient in front of R instead of a division. That would just make it a little bit simpler, which would be 13.16 times R. And there is our expression. That's our end goal. Okay? So our next step, it would be to take that expression, and we're going to use it in Logger Pro to fit that function to your data. So we're actually going to do a manual fit. So when you come back on Monday, we're going to do that. And then we'll also do it for the spherical Gaussian surface, and we're going to see which geometry is going to fit that best, fit the data the best, I should say. Okay, so your job right now is to do the same type of derivation, but you're going to be doing it for a sphere. So if we go back, instead of using a cylinder Gaussian surface, you're now going to use a sphere. That's going to change your equation for your electric field. And then you will use this expression, put the electric field you derived using Gauss into that electric field right in that equation. You're doing that same operation and coming up with an expression for your electric field, your potential as a function of radius using your field that you found using the spherical Gaussian surface. All right, good luck. And I look forward to seeing what you came up with on Monday.